Hi, I am Dr. Abhishek Joshi, and today in this video lecture we are going to discuss about the digital modulation scheme, that is PSK, that is phase shift keying. So we'll discuss what is phase shift keying and then how we will generate the phase shift keying and how we will recover back our message signal from the phase shift modulated signal. So in phase shift keying, so according to the name, P stands for phase shift keying is PSK. This means the phase of the carrier phase or the phase of the carrier is changed in accordance with the message or the data signal. So message in digital, we know that it is represented in form of zeros or ones. This means if we have 0, when we are talking about binary signals, if we have 0, this means we will be having one phase, it may be a 0 degree. And if we have the 1 data as 1, this means we will be having the phase of 180 degrees. So there will be a phase shift in case of binary, when we are especially we are talking about the binary phase shift keying. We have either 0 or 1. So according to 0, according to the data 0, we have 0 degree phase difference, and 1 is represented by 180 degree phase shift. So if a baseband signal MT, where the polar and the corresponding modulated signal, so we are representing the corresponding modulated signal that is given by MT cos of omega ct, where omega c is the carrier angular frequency, which can be written as, that is omega c, that is given by 2 pi of fc, where fc is the carrier frequency, would appear in the figure B. So it is given in the next. And in this case, if Pt, so we are representing Pt is the basic pulse. So Pt is our data pulse, or it may be basic pulse. So in digital communication, we are using the rectangular pulses, but these are not the practical pulses, these are the ideal pulses. So pulse may be having any shape, it may be a sinc function. So according to the Nyquist criteria, which we have discussed in our previous lectures, you can go through the previous lectures and you can understand why we are not using the rectangular pulses for transmitting our digital data. So these pulses can be having any shape like sinc function, or it may be having some slope according to the roll-off factor of the Nyquist pulses. So this is the basic pulse. We are transmitting 1 by the pulse Pt. So we are giving the shape, that is Pt cos of omega ct, and 0 we are representing it by minus Pt cos of omega ct. So or we can write in other ways, there is a 180 degree phase shift. This means this is Pt cos of omega ct plus pi, representing the 180 degree phase difference. So if it is having 180 degree phase difference, this means it can be written as, so cos of pi can be written as minus of cos. So minus Pt cos of omega ct. So same is written here. As we can see, it is written here, that is minus of Pt cos of omega ct, that is equals to Pt cos of omega ct plus pi. Okay. So hence two pulses that are pi radians. In radians we are representing it as, that is pi radians, or you can say 180 degree, are apart in phase. So phase is representing our data, that is 0 or 1. So the information resides in the phase or the sign of the pulses. So for this reason, this scheme is known as phase shift keying. So that's why we are calling it as a phase shift keying, and that is a reason. Now note that the transmission is still polar. This means we are using either plus or minus. We are representing voltage as plus V or minus V. Okay. So depending on that, we are calling it as a polar signaling, or you can say it's having both the polarities. So it is polar. So in fact, just like ASK, PSK modulate carrier signal has the same form. So we can write the PSK modulated signal that is given by phi PSKT, that is equals to mt cos of omega ct, and the message can be written as, that is mt equals to summation ak is the strength of the pulse, and this is represented by the pulse train, the pulses which we are using to transmit our data, with the difference that the line code is polar in form. So if we are using a polar signaling, we are representing 0 by -1 and 1 by +1. So if we are using the polar signaling, we can easily modulate our carrier signal. We can represent our carrier signal as a cos of omega ct. We can represent our carrier and we can multiply our carrier with a polar signaling, and the multiplied version is the multiplication of these two will give you the PSK modulated signal that are 180 degree, or you can say out of phase, 180 degree phase shift or out of phase. So it can be represented graphically as, so let's assume that this is our data, or you can say message signal. Now this data or the message signal is multiplied with a carrier. So here I am drawing one carrier for representation. With respect to time, and this is nothing but a carrier frequency, or we can write it in form of mathematical equation, that is a cos of omega ct. Okay. Now this is our data, this is our carrier. Now we will multiply these two, and the multiplied version is nothing but the PSK. Okay. So here we can see, here we have the voltages as +1 and +V, or and this one is -V. Okay, it may be +1, it may be +5, it may be +10, it may be here, it may be -5, it may be -1. So negative voltage and positive voltage representing the polar signal. So this is the NRZ polar signaling. In the NRZ polar signaling, we are representing our data as 1 by plus voltage and 0 by minus voltage. So when 1 is multiplied with this carrier for this duration, let's take this duration. When 1 is multiplied by this duration, what we will get? We will get the same thing. 1 multiplied by any quantity will be the same quantity. Let's assume it is as a 1. Okay. So we have the same, means there is no phase difference. So there is a phase difference, or you can say phase shift given by 0 degrees. So when we have the -1, so -1 multiplied by the carrier. Okay, so what we will get is, we'll be starting it from, means when we have +1, we will start from 0. We will start the pulse from 0. When we have 0, this means -1. So -1 means 180 degree phase shifted. So our carrier will start from, or it's having 180 degree phase difference. Okay. So similarly, we can see here, if this is the modulated, or you can say the carrier signal. Okay. So here we can see it is starting from 180 degree. So 180 degree phase difference. So here we will be having, at this point we will be having 180 degree phase difference. Now again we have the next one. So 1 multiplied by quantity will be the same quantity, means there is a 0 degree phase difference. Next again is 1. So 1 multiplied by the carrier, we will get the same thing. So there will be no phase difference. So here we can see, here we have 0. 0 is represented by -1. So -1 multiplied by the carrier will be having the 180 degree phase difference. Okay. So here we will be starting from, so 180 degree phase difference. So next again we have 0 by -1. So again we will be having the 180 degree phase difference. So here we can see 180 degree phase difference. So next again 180 degree. So there is no phase change. Continuously we have 3 zeros. Now we have 1 here. So 1 is represented by +1. So we will start from 0 degree phase difference. So here we have the changes. So phase is changed here, here and here. Okay. So accordingly we can see that when there is a change in the bit, or the bit is reversed or the bit is flipped, then there will be a phase change or phase difference that can be observed by the Psk modulated signal. So I think the concept is clear how this Psk or the phase shift keying is done. So the modulating signal MT and the phase that is represented by the Psk modulated signal, that is MT cos of omega Ct. So now we can write the orthonormal basis function, or we can find the orthonormal basis function for our signal, that is given by A cos of omega Ct. So we have represented our signal, that is S1t, as A cos of omega Ct, and S2t we are representing it by minus of A cos of omega Ct. So both the signals S1t and S2t are having out of phase or 180 degree phase difference. So we know that how we can find the orthonormal basis function. So it is given by, that is phi it, that is given by SIT divided by under root, or you can say GIT for generalized case, and it is given by the energy of GIT, that is the intermediate function. So Gi square t dt for the range 0 to t. Okay. And what is the intermediate function? Intermediate function is given by GIT, that is given by SIT minus summation j is equals to 1 from I minus 1 to I minus 1 Sij and phi j t. So this is how we can find the intermediate function, and we can find this coefficient, that is Sij, which is given by integration Sit into phi j t dt. Limit is from 0 to t. So we can find the basis function phi I t using the intermediate function. But here we can see that both the signals are not linearly independent. So when the signals are not linearly independent, this means the number of basis function, if we have the n is the number of basis function, is less than the number of the message signal, where m is representing the number of message signal. So we have here m equals to 2. So this means n will be less than 2, and n is always an integer. This means we have only one basis function, that is phi 1t. So when we have only one basis function, this means we don't have to find the GIT. Directly we can write GIT as SIT. Okay. So this means our formula will reduce to, that is phi 1t. So phi 1t we can directly write it as, that is S1t divided by under root of the energy of S1t. Okay. So here we have to find the energy. So S1t, here we can see it is given by A cos of omega Ct. So S1t is given by the energy of S1t, or I can write energy of S1t, that is given by 0 to Tb cos of, that is A cos of omega Ct. So A S1t is given by A cos of omega Ct whole square dt. This means we can expand it as from 0 to Tb for single bit duration, A square cos square omega ct dt. And we know that this is the trigonometric identity. Cos square can be written as 1 plus cos of 2 omega ct by 2. So substituting this, we'll get it as 0 to tb a square and 1 plus cos 2 omega ct by 2 dt. So we can expand, or we can open this bracket. We'll have, or we can take this coefficients outside. So this a square we can take outside the integration because this is a constant term. 2 is a constant term. So what is left inside the bracket? So we'll taking this integration inside. So it from 0 to tb and dt plus integration 0 to tb cos of 2 omega ct dt. So this integration will result 0. If you integrate it, it will be 0. So what is left is, that is energy of S1T is given by a square by 2 and integration, that is upper limit tb minus 0. So what we'll get is energy as a square tb by 2. So this will be the energy of the pulse. Now substituting this energy in our equation. So phi 1t. So here we have phi 1t. Phi 1t is given by a cos of omega ct divided by under root of this quantity, that is the energy. Okay. Substituting this in phi 1t, we will get phi 1t as given by S1t, that is a cos of omega ct divided by under root of the energy. Energy is given by a square tb by 2. So this a square and this a will be cancelled out, and what is left is, that is root of, we can take it in the numerator, it will be 2 by tb cos of omega ct. So this 2 by tb cos of omega ct will be the basis function or orthonormal basis function for BPSK signal or modulation. So we can finally define, so in the PSK pair of the signal, that is S1t and S2t, used to represent binary 1 and 0 respectively, where this S1t is given by under root 2 EB by TB cos of 2 pi FCT. Okay. So how we are writing this amplitude as energy? That is, here we can see it is written, it is given by, energy is given by a square tb by 2. So energy is given by, if energy is given by a square tb by 2, so we can write amplitude in terms of energy is twice of energy divided by tb will give you the amplitude. So we are writing a as in terms of energy, that under root of 2 EB by TB cos of, so here we have a square term, so we have under root here. So 2 EB by TB cos of 2 pi FCT. And the second signal is represented by under root of 2 EB by TB cos of 2 pi FCT plus pi, because there is a 180-degree phase difference. So if you have 180-degree phase difference, it is given by minus of under root 2 EB by TB cos of 2 pi FCT. So S1t and S2t are referred as the antipodal signals because both are out of phase. So one can describe this scheme of modulation as one-dimensional modulation scheme, where one basis function, so we have already got the basis function, that is one basis function phi 1t, that is given by under root of 2 tb by cos of omega ct. So here we have written the first orthonormal basis function, that is phi 1t, that is given by under root 2 by tb cos of 2 pi fct for the bit duration, that is from 0 to tb. So finally we can represent our BPSK signal in the signal space diagram, or we can say it as a constellation diagram. We can call either it's a signal space diagram or we can call it as a constellation diagram. So the transmitted signal in terms of S1t and S2t in the terms of phi1t, that is given by the basis function, that is S1t, that is given by under root EB phi1t, and we are representing the second signal, that is S2t, that is equals to minus of under root EB phi1t. So both are represented using the same orthonormal basis function for the entire bit duration, that is from 0 to t. So if we are representing, that is phi1t on this axis, so we have this phi1t, and here in this phi1 we are represented the S1t, that is given by, or this is the first message point, so this one will be the S1t, and this one is the S2t, represented by, here we can see we have the negative sign, so it will be on the left. So here it is represented by minus of root EB, and S1t is having the positive, so here we have the plus of root EB for the regions, that is region Z1, here we have the region Z2. So we are drawing a decision boundary between these two message points. So this is the message point 1, this is the message point 2. We have the decision boundary will be the passing through the origin or the center. Okay, if we calculate the distance between these two, so half of the distance between these two will be the decision boundary. So here we have S1t represented by this diagram, that is given by under root of EB by TB, that is for the positive, and for the negative for the entire bit duration from 0 to TB. Similarly, we have defined S2t, that is 180 degree out of phase. So similarly, it is given by this. So we have the decision boundary, and we have represented our message point in the constellation diagram of the PSK signal, that is signal space diagram of PSK. So a coherent binary PSK system is characterized by having a signal space that is one-dimensional, that is n equals to 1, because we have only one basis function, with a signal constellation consists of two message points, that is m equals to 2, that I already explained you, and the coordinate of the message point can be written as, that is S1t. So we have rewritten in terms of how we have calculated it, that is from 0 to TB S1t into phi1t dt, that is given by plus of root EB, and S21 is calculated as from 0 to TB S2t into phi1t dt, and we are getting as minus of EB. So this is the mathematics of how we calculated plus root EB and minus root EB for representing the signal space diagram or the constellation diagram. So how we can generate the PSK signal? So we can generate the PSK signal as, that is a binary data sequence, and it is the polar non-return to 0 level encoder, and this is the product modulator. So product modulator, we are multiplying the polar NRZ encoder, and we are multiplying it with a basis function, that is phi1t, that is given by under root of TB cos of 2 pi ct, and the multiplication will result you the BPSK signal. So this is the BPSK signal. So in binary PSK, 1 is transmitted by a pulse a cos of omega ct, and 0 is transmitted by a pulse that is minus of a cos of omega ct, which we have seen in the figure in the previous slide. This is the previous slide. And the information is PSK signal therefore resides in the carrier phase only. So just in the DSBSC, that is double sideband suppressed carrier, these signals cannot be demodulated by the envelope detection, because the envelope stays constant for both 1 and 0. So the non-coherent, or you can say the coherent detector for the binary PSK modulation scheme is shown in the figure. So at the receiver side, we can use the coherent receiver, where we have the received signal, that is a PSK modulated signal, multiplied with a basis function, or you can say the carrier, and the multiplication is given to the low pass filter, or it is represented by integration, that is from 0 to TB dt, and we are getting here the pulses, that is x1, and here we have to take the decision after filtering out the higher frequency, passing only the lower frequencies. So we are having these pulses. Now here we have to take the decision. So decision boundary will be here, and we are putting the threshold at 0. So if the value is greater than, if x1 is greater than 0, then we will call it as 1. If x1 is less than 0, we are calling it as 0. So we are putting threshold at 0. So at the receiver side, we can easily receive our pulses. So at the detection can be represented mathematically by a plus minus a cos of omega ct, and we are multiplying it by 2 cos of omega t, passing through the low pass filter and taking the decision, we are getting 1 and 0 respectively. So we have using the coherent binary PSK detection that is similar to the DSB-SC as we have seen in analog modulation schemes. So we can write the power spectral density in the mathematics for the PSD of BPSK, that is given by GT is given by under root 2 EB by TB for the entire bit duration from 0 to TB or 0 otherwise. So the power spectral density of the BPSK modulated signal, that is SBT, is given by 2 EB sin square pi TB by f and pi TB f whole square and 2 EB sinc square TB by f. So finally we can represent our power spectral density of carrier. This is for the carrier, and this is the power spectral density of the BPSK signal, where we have represented the imaginary frequencies as well as the real frequencies. So here in this third diagram we have represented by the real frequency only. So here we can see the carrier is representing by the sinc function, where because our data is representing the rectangular pulses, and we know that the Fourier transform of the rectangular pulses is the sinc function. So the Fourier transform of the data will be the sinc function, or you can say the pulse train PTB. And here we have now when we multiply it with the carrier, so multiplication will result, so it will be shifted by the carrier. So whatever the carrier is, so here we are the frequency, that is the DC shifted to the carrier frequency. Okay, and this sinc function we can see at the center frequency f0. So if we are concerned only about the real frequency, so real frequency is given by this figure, third one. So in this lecture we have discussed how we can generate the PSK or how we can modulate a PSK modulation. Similarly, we have discussed how we can demodulate a PSK modulated signal, and we have discussed about the power spectral density of the BPSK, especially the BPSK signaling. So here we are going to stop the lecture. Thank you.